This conference will now be recorded.
Okay, welcome everyone. Today we have a relatively packed schedule. So we'll start with Julian. He's going to tell us about a new work stream, which is about measurement and instrumentation. And after that, we'll see if DJ comes, we will have a short presentation about sustainability in OCP. Then we'll have Georgi talking about the API workstream, which is, I think, the third workstream. And last but not least, Gary will tell us about the latest for the oscillator workstream. So with no further ado, Julian, let's set you up as a presenter. Let's see if that make a presenter. Okay, Julian.
Yeah.
And I see also Anand is on the call.
Yeah, Matt.
Great.
Sorry,
Let's get started.
Okay. So I'll share my screen and we'll share the slides. So I'm presenting on behalf of Anand and myself. So as part of the OCP conference or you guys can see my screen, right? You see the screen?
Yes.
Okay. So as part of the OCP conference last week, Anand and I worked on coming up with a vision for a measurement and instrumentation workstream as part of OCP TAP. So the main goal of this is to create an ecosystem of measurement hardware and software that anybody can use and develop on top of. So the general idea is to have a tiered structure, kind of like the oscilloscope market was my idea, where you have an economical, mid-range, and high-end. Some initial ideas for what would be in this workstream would be client gen, which is basically just a PTP traffic generator that could be run on any NIC server combo that supports PTP, and then one PPS measurement hardware. So that could be anything with TDCs or FPGA, NICs, DPLLs, anything that supports one PPS measurement, and GPS. And then we were discussing what would be an early proof of concept for this workstream, and one idea was to use the time card and a NIC to create a test system. So similar to the Paragon Neo, where it emulates a master and a client on a single box and then measures PDEV and other PTP parameters. And then another proof of concept on the software side would be to hook in time card for PPS measurements and basically use the existing CalNEC software to analyze those PPS measurements on the time card. So this is the general idea so far. So we wanted to open it up to any ideas or suggestions that anyone might have, so we don't get too off track, and that we make sure that whatever we develop will actually be useful to the overall industry. So Anand, if you want to add anything too, please feel free.
No, I'm in a pretty noisy place, and you did a fantastic job. So nothing to add. Thanks.
Thank you. So if you have any ideas or anything that you would like to see developed, please reach out to Anand or myself. Anand is listed as the workstream owner on OCP on the Time Appliance Project wiki page. So we're looking forward to any collaboration that anyone is willing to put forth. Thank you.
Thank you, Julian. So let's go next. We have DJ or Dharmesh. Let's see, I'll make you a presenter. Make a presenter. DJ, are you ready?
Yes, I'm ready. Can you give me presentation access?
Yes, I did. I just did right now.
I got it.
Wonderful.
Can everyone see the
Yes.
presentation? Perfect.
Yes.
So, hey, Ahmed, thanks for having me here. I'm part of the sustainability group. As part of the incubation committee, we launched sustainability and circularity as a strategic initiative in 2021. And I wanted to give first a quick update to the your project, this project team on what we are doing, and more importantly, in 2022, we are going to start working in cross-functional fashion with other projects, and we would love to do that with you all as well. So at the beginning of 2021, incubation committee went through an exercise to figure out what are the key problem areas which industry is facing, which we need to solve. So until recently, until 3 years back, Open Compute was involved in looking at companies contributing the solutions and building open community. Starting about 2.5 years back, we started changing the way incubation committee operates by identifying and focusing on problems which the community need to solve rather than contributions which come organically. So the 2021 exercise led to following areas. We identified developing integrated solutions as one of the areas where community should work on, because OCP adoption is very important. Sustainability, circularity, and then data center facility security, and few others. I'm here to talk about sustainability and circularity. So the main goal here is that we want to move towards science-based targets for alignment with Paris Agreement and trying to build sustainable data centers which are aligned with the global protocols. That's the bottom line. Because when you look at the carbon emission, data centers are one of the big carbon emission contributors for any of the companies which are running these data centers. So carbon emission is identified as scope 1, scope 2, scope 3, which are just 3 different ways in which company operations lead to the bottom line of the carbon accounting, which the company is responsible for, and running a data center operation becomes one of the big factors. So the idea which we are pushing with OCP sustainability and circularity is, first, we are in the first year of getting this launched, so we want to start promoting awareness about this particular area. Many of you attended OCP summit last week, and sustainability was front and center. So this is in great part to the work which this particular work stream has done. Next, we actually want to start doing something concrete. We want to identify key steps in component design which basically make products reusable. So let's say you are designing a timing card, and can you make sure that we do certain design principles which make this timing card life cycle longer than 3 to 5 years. It can be reused in many areas, right? That leads to a lower carbon footprint. And then we want to also look at the way we do the measurements itself. Life cycle analysis is one of them. Hardware efficiency analysis is another one. So these are all the goals which we are working towards. And in 2022, this is going to become a full-fledged project. So OCP sustainability and circularity initiatives milestones. In 2021, we started the work, and then we went through the whole year leading to a big launch in November summit, where over 14 presentations, multiple panels, and companies from Google, Microsoft, Meta, and everybody else was involved in presenting their outlook, right? So that's one of the areas which we worked on. And then in 2022, we also launched 2 substreams. Like we launched measurements and LCA analysis in March, and we launched life cycle extension, which is a way to prolong the life cycle of component, right? So one is how to do the measurements, and the second one is how to make things more circular, and that's what we are working on. So I won't go into this, but this has already happened. We also published a white paper, which is another first for OCP. This is the first time a sustainability-centric white paper has been published in OCP through work of collection of companies. And then we are also working to basically talk to the entire project streams across OCP. So as you can see, for timing appliance, I've given my name, and we have already completed a whole bunch of conversations with servers, security, rack and power, etc. And again, the goal is we want to find a tiger team. We want to form tiger team which has a cross project representative, so that sustainability becomes a very fundamental aspect which all of you think about every time you're thinking of your design. You could be thinking about it in terms of making things circular. You could be thinking about how can we do things to do the measurements, which can help in sustainability. So those are the things which basically we are looking at. And then very quickly, the overview of the work stream itself. As I said, there is matrix and life cycle assessment, which happens every 2 weeks. And similarly, we have a circularity work stream, which happens every 2 weeks. And then we have an overarching monthly meeting, which brings everybody together, and it happens once a month. So it allows for cross-pollination across all of them. And each of these work streams have specific goals, objectives, which we are working towards. And eventually, we want to even bring sustainability as the 5th tenet within OCP, which will be a very big step for OCP. As all of you know, OCP has 4 tenets in last 10 years, and adding a 5th tenet is not trivial. But we feel very strongly that bringing sustainability as a way to measure all contributions becomes very critical, and that makes everyone think about it. So 2022, that's one of the goals which we are trying to do. And then we have certain goals on each of these work stream which we are already working on. And the idea again is that we want to start forming a tiger team from each of the projects which are in running, so that we can collectively start feeding sustainability as a core idea across projects. And also anything which we are working on, we can take advantage of the knowledge which you have to see if there are things you could contribute into it. How do you do a better measurement, or how can you do extension through circularity? Perhaps we can leverage that cross-functional knowledge. So that's basically what I wanted to share. We also have a goal for 2022. As I mentioned, we are planning to make sustainability as our 5th tenet, presenting it to board by middle of next year, and then work longer term so that we can all achieve net carbon zero by 2030, as many of the organizations have. So I wanted to stop here. I basically, I wanted to take this opportunity to share that this particular work is happening in OCP. It's a cross-functional work, meaning it's not a work like server, which only deals with server design, but this is a sustainability, which is like security, or it is like hardware management, which spans across all of the project areas. So I wanted to take, no more than 10 minutes. I'm going to pause here and see if there are any questions.
So I have a
Thank
question.
you, DJ. Yeah.
Can I ask a question? Or?
Yes, absolutely. Go, Hisham.
Yeah. So for just what is the relationship between sustainability and the TAP project? Are you talking about how the TAP project can reduce energy consumption, for example? How you develop the board or the card? How what technologies you put into?
Hisham, this is more like we're advertising all our sister projects, basically, like in OCP. So this is another, like, this is a project adjacent to, let's say, TAP. So the same way like we basically present in other OCP projects about TAP. So
exactly, because not many people know about this project, right? Just like not many people know about TAP. So and then there could be ways in which, for example, TAP can provide technology into a server or a networking device. Similarly, sustainability can be considered in design of TAP-centric products, right? And it is not just related to energy consumption. It could be related to, as I mentioned, that currently there are 2 substreams, right? One is how do you do measurement? Simple as that. There is no improvement discussion, just life cycle analysis measurement, or how do you do efficiency measurements? That could be one thing which can be discussed even inside TAP, right? And the second is, how can we extend life cycle of various devices? And these devices could be servers, these devices could be networking switches, these devices could be timing cards, which you guys are building. These devices could be storage servers, these devices could be OEM. any of these devices, how can we go from 3-year life cycle to 5-year life cycle, or make it reusable? Meaning, when one company or one data center decommissions gear, how can it still be productive in the second life by another set of customers? And for that, a lot of things have to be thought through in terms of how the firmware transfers, how the certificates, security, ownership, all of that needs to be worked out, because sometimes devices in one data center have certain type of software running on it or firmware running on it, which is very customized for that data center or that particular customer. Now, when you decom that gear, how can somebody else take advantage of that hardware when they don't have access to the same software or firmware, right? So those are other areas which we are looking at solving. So it's not just about energy.
Yeah, awesome. Thank you very much. Okay, if you have any more questions, you know where to find DJ. So just like on the OCP page, just go for the sustainability project. So let's go for the our third item, which is Georgi is going to talk about the API workstream. Georgi, let me make you a presenter. Okay, Georgi, you are the presenter. Your audio is multiplied by 0. Okay, now it's open.
Am I the person not presenting?
Yeah, you are the presenter, yeah.
Okay.
Just looking at the slides.
Let me find the slides. Okay, can you see my screen?
Yes.
And let me find how to get rid of this. Oh, okay, I think that's good.
Wonderful. Let's do it.
So this is going to be really, really short. I had a presentation on the summit. You can go back and look the presentation. But the goal of the today's short announcement is focused mostly on the API side. We have an environment where we have a lot of effort on the hardware side to make sure that the time uncertainty is managed across the different stages of the PTP, and we can get the grandmaster and the ordinary clock to be in the range of a few hundred nanoseconds difference. So the time uncertainty is strictly below 1 microsecond. But when we get to the software stack on the right side of the slide, we have a lot of layers, and every one of these layers introduce a certain level of clock uncertainty. The problem is not that this clock uncertainty is too big. The problem is not, it is poorly defined. And we might expect not only the PCI bus to introduce time uncertainty, but also the driver itself, the Linux kernel, the way that the Linux kernel schedule the threads in the user layer. And at the end of that, on the top of that, we have application that needs to get the time and the time uncertainty in a certain point, and it is very difficult for the application to reason about time uncertainty. We know that some companies solve this one way or another. The goal of this stream in TAP, the third one, is to unify the approach we have on the application layer to get data from the NIC that allows making decisions based on the clock and the time uncertainty. The decisions are not necessarily limited to the clock itself. We might need to propagate more information that the servo, for example, provide, or when was the last time when we had proper synchronization of the PHC, and all this information today we would love to push up to the application through some kind of unified API. I'd like to invite you, those of you that are interested to discuss the software stack, let's get together and find how we can make the API level, API on the application level useful, usable, and desirable. I'd like to discuss with more people what is the right way to propagate this information up through the layers. And together we can come with a proposal that eventually can be the new time API, a time API that's not limited to just a number, but provides variety of different attributes that allows making decisions and using time in distributed systems. I'm going to post an URI, a link to the web page. You can go to the web page, and if you're interested, please send me an email. I will invite you to the next meeting where we can discuss more. Please send me not just the email, but also the time zone you are in, so we can find a good time for a meeting. Thank you.
Thank you, Georgi. Is there any question? Gautam, do you want to add anything, or it's all good? Is Gautam still here? Okay, great. And Georgi shared also a link to the wiki. You can get there. Okay, so last but not least, we get now to Gary's presentation. So let me make Gary a presenter. And I think I will save the time for the bio and everything. I make everyone knows Gary, and I give more time to Gary for his presentation. So Gary, the floor is yours.
Okay, thank you. Can you guys see my screen?
Yes.
Awesome. There's just, hold on, I need to move the GoToMeeting stuff out of the way. Okay.
Minimize, yeah, good.
Can you, is it showing as a black box over my shared screen or no? You can see that, okay.
It works, yeah. It shows your desktop too. So anyways.
Yeah, on the only on the bottom, right? It doesn't show the GoToMeeting controls.
No.
Okay, can't figure out how to minimize that. Okay, so let me just back up. The goal of today's meeting is to give an update on the oscillator workstream. This is a work stream with several other participants from the industry and oscillators and other companies that we've worked with over the last 6 months. And the goal here is trying to summarize what we've done and generate interest, and also to collect feedback, not just in this meeting necessarily, but by inviting people into the oscillator workstream meeting, which is Wednesday mornings at 8 a.m. Pacific time. We'd love to have more people contribute and get everybody's feedback. So today, let's just talk about what we've done. So the agenda is going to be, why do we have an oscillator workstream? And that's going to lead to a motivation for having oscillator classes, so classification of different oscillators for different nodes in the network. And then part of that is not only the specifications which create these different classes, but the test methodologies used for the test specs. In particular, holdover is the main concern here, and we're going to go into an overview of the methodology, sort of the framework that we're using at a very high level to calculate a holdover methodology. And we won't provide all the details today. If you're interested, please do contact me. My email is on the OCP TAP wiki page online. And then finally, I'll have a question that I'll pose to the group at the end, and then the call to action. So why do we have an oscillator workstream? The issue is that there's many different nodes that require different classes of oscillators, like the grandmaster, the ordinary clock, and transparent clock. They all have different requirements from an oscillator perspective. And when people look at an oscillator data sheet, they don't exactly know how to map that into the requirements for each of these nodes. It's difficult to select the oscillator class. So we're going to make that simpler by introducing classes for these different use cases. And like I mentioned, not only are we going to create specifications for these classes, but we're going to create specifications for the test methodologies where it's important. And just to give you an idea, so we have this, I apologize, there's just a lot of GoToMeeting controls I have to navigate around. We have this document that we're continuously working on, that's the specification for oscillator classes. And part of that document, we have pretty well nailed down that we have a few open items for normative specs for standard data center environment, open grandmaster that doesn't have synchronous Ethernet. And you can see that this is the spec table here, where we call out things like ambient temperatures, frequency stability over temperature, Allen deviation, all the things that you would expect to see for an oscillator specification. And with various footnotes to indicate how these are measured or test conditions. Of these test specs, the most difficult to satisfy is the holdover specification, of which there's two. We have a 24-hour holdover spec of 1.5 microseconds and a 1-hour holdover spec of 250 nanoseconds. And it looks innocent enough, but actually when you start digging through what is a holdover measurement and how do you measure it, and we're giving a number here, but there's always going to be some population that falls outside of that. So how do we quantify that? And that leads to the next section, which I'm going to talk about, which is the holdover test methodology. And part of that test methodology is requiring the standard to set different inputs that go into the test method. And we're going to specify those as two separate test specs. One is the test spec for different classes of oscillator. Each one of those classes, which is of course use case dependent, will need to specify what the holdover time is, what the thermal profile for that particular node will see, what the operating ambient temperature would be, what are the ambient temperatures that were required to measure aging and frequency versus time, what is the acceptable probability of error. So for grandmaster, maybe you require 6 nines of accuracy, or not accuracy, 6 nines of the population, so 99.9999% of the oscillators shipped should meet this requirement. And maybe in the ordinary clock, you have a different requirement for the probability of error that the system can live with. But that is very important for us to understand what level of quality we need to ship to. The training time that the oscillator requires before it enters holdover, so that we can get an average frequency for initial frequency offset when we're entering holdover. And of course, we need to have some sample unit population defined. So we don't want a population of 1. We want something that's higher than that, but not too high that it becomes a burden. So for example, 10 random units for each of 3 lots having a different process and assembly is one recommendation that we have now. And then to capture the random events, we need to have a trial population, which I'm capturing as capital M, meaning that for every time we measure the output of an oscillator, if we repeat that same measurement for that same oscillator, we're going to get a different result because there's a wander characteristic, which is this random variation of frequency at the output. So we need to quantify that as well through this trial population. And then if the system compensates for aging, we need to know that so that we don't count aging against holdover, because holdover shouldn't include aging in that case. So these are the inputs that the classifications of oscillators will all contain, and the values will change depending on the use case, depending on the class. And then we'll have a separate specification just for how we measure holdover, the test methodology, which will use those previous slides as an input. Yes?
I have a quick question. You said compensate for aging, but you didn't put anything for temperature in there as well. Just wondering, is it just because you're figuring it whatever the temperature variation is, it doesn't need that within a data center, or?
Yeah, whether the oscillator compensates for temperature or not, I guess there's multiple paths to get to the end result. What the end result is the holdover value. And if you can get there without compensating for aging or with compensating for aging, for temperature, then I suppose it doesn't really matter. But the way that I'm going to build out the model, is going to talk about the different noise sources. Aging is one, thermal variation is another, and I think, at least when you say compensating for temperature, I'm thinking about it like a TCXO or an OCXO.
I'm thinking more the system actually is measuring something.
I see. Okay.
But I'm not sure it is relevant given the small temperature variations. I don't know you can make much of it.
Yeah, I see what you're saying now. The way I was approaching your question was we don't want to specify whether it needs to be a TCXO or an OCXO.
Understood.
Yeah.
Got it.
But at the system level, if that does improve things, then maybe we can include that inside of this discussion as well. I hadn't thought about that. It's a good point.
Hey, Gary, one question on your previous slide in the table. Can you remind us again where the 1.5 comes from?
Where's 1.5?
In the previous table.
Oh, in the specification table.
Yeah, for the holdover.
I think you're going to mention the number should be 1.4. Is that where you headed, Michelle?
Yes.
Yeah. So the 1.5 came about many months ago when we were asking for what the requirements were for a data center, and somebody mentioned the value of 1.5. That's where it came from. If the correct value is 1.4, we can adjust to make it 1.4. Essentially, that value should be whatever the data center, whatever that particular node requires.
Okay, I think what would be good would be to correlate what was done during the development of the profile, and then that number would be of use in your table, and vice versa. That's something we can discuss in your oscillator work stream. Yeah,
I agree, and I think maybe that number 1.4 came out after we had already picked the number of 1.5. We'll go back and we'll revisit, but you're right. We should be on the same page, so we're consistent.
Thanks.
Okay, so looking at how we specify the holdover test methodology, when it comes to holdover, particularly 24 hours of holdover, 24 hours is a long time, but when you're looking at a device like an OCXO or a TCXO, if you look at the datasheet conditions for holdover, there's always a preconditioning time to allow the oscillator to settle. And that could be typically 30 days. So any holdover measurement is going to be at least a month to make. And these parameters here that define the classes, these are going to change, of course, and depending on the operator, they may change. There may be a lot of variation. So there may be many different classes. Each class is going to trigger over a month of testing for holdover. So it's conceivable that there could be, many different classes, each one are having a different temperature profile, different operating ambient temperature range, and so on, which leads to a lot of measurements in the laboratory. So when we set up the holdover test methodology, we wanted to create a methodology that would allow us to go into the lab once and do some measurements, and then from there on after, allow us to post-process the data to meet all the various needs for these classes. So the methodology we developed is a statistical methodology that requires two simple measurements. We need to measure frequency stability over some ambient temperature range, which is a fairly straightforward measurement. And then we also need to measure frequency versus time at a given temperature, plus or minus some margin, so within a few degrees. Both of these are fairly straightforward measurements the oscillator vendors do today. And then based on those two measurements, we go in and we post-process the data using MATLAB or other tools. And from that, we extract the daily aging, we extract the thermal drift and the wander from the measured data. And then we build up these distributions there, and we model them as Gaussian distributions for aging, thermal drift, and wander. Wander includes not only the natural variations when you're in holdover, when you're inside of holdover, but also the initial frequency offset entering holdover. And each one of these we can characterize as a distribution with a mean and a standard deviation. And then we can combine those in some intelligent way to create what I'm calling Emax here, which is the maximum time error up to and including the holdover time that's specified by the class tau sub h, and for a given probability of error, p sub e. That's ultimately what the oscillator vendor is going to report in order to show compliance to each one of these classes. Then if the oscillator vendor requires additional test conditions, such as requiring a cover or some keep out restrictions for the mechanical design of how to design in their products, then those should be stated as well, just so everybody knows how to reproduce the results that the manufacturer has obtained and is showing compliance to. So that's the big picture thinking about how we set up the holdover test method. And then in terms of the implementation, here I'm just showing that we're looking at a population of n units for aging. The reason for that is every unit will have one aging number. There won't be any variation. If we repeated the aging number for a particular unit, we'll get the same result. So we build up a population of n units, and from that extract a mean and a standard deviation. And we do the same thing for thermal drift. There's also going to be n units. So the thermal drift is a characteristic of the part. Once we measured it once, it won't change. But wander, it will change depending on when we measure the part. Every time we measure it, there will be a difference. And so we build up a population of n units times m trials per unit. And we also pick off a mean and a standard deviation. And then from that, we can calculate based on Gaussian statistics. It's been around for many decades now, that if you combine statistically independent processes and they're all Gaussian distributions, that the n distribution will also be Gaussian, whose mean is the sum of the mean of the individual noise contributions and whose standard deviation is the root sum square of the standard deviations of the individual contributors. And we'll end up with a distribution that itself is Gaussian. We'll have some mean value and some standard deviation, and that will characterize our total maximum time error at a given time tau sub h. And then we can take that equation and we can convert the standard deviation, which is essentially a 1 sigma value, which captures 68% of the population, and we can multiply it by this, what I call a crest factor, Q of x, and that converts the RMS value into a peak value that allows us to walk down the Gaussian tail and stop in the Gaussian tail at the location specified by the probability of error called out by the class specification for that oscillator. And so there's two possibilities. We can have either the mean value for the total population is close to or equal to 0. We call that a two-sided distribution, or it's somewhat distant from the mean value being 0, in which case we call it a one-sided distribution. And the statistics are very slightly different, and that's why we have this lookup table for each of these cases. I don't know a priori which one of the two we'll always see, or if there'll be a mixture, so I'm just covering both cases here. But essentially, this is going to be a lookup table based on the probability of error that's called out by the standard and by the particular class. We look up the value. So for example, if the mean is centered around 0, and then we want to look at 6 nines, then we have a value of 4.892. But if the mean of that total error distribution is centered around 0, then it drops to 4.754. And we simply use that as a multiplier to convert the standard deviation into a peak value that we can then add to the maximum offset, the mean value, and calculate where that Emax value is sitting on that distribution. The way we would interpret this value of Emax is that, typically in the oscillator world, we characterize holdover on a per device basis. But here, when we're looking at standardizing it, we have to calculate it for the entire product line. So it's ensuring that if we ship lots of units, that each one of those units will meet the value of this maximum time error up into and including the holdover time for a given probability of error P sub E. That's really how we interpret that value of Emax. Now, I wanted to kind of illustrate this in a different light, which is if we're looking at the value of Emax versus time when we're entering a holdover, and this graph begins where we're entering a holdover essentially, we have this dashed line which indicates the mean value of our distribution of Emax. And then on top of that, we can go up plus or minus 1 sigma, and that's these fainter, I guess, purple line. But really, we don't want to go out plus or minus 1 sigma because that's 32% error that we're shipping. We want to go out to the specified probability of error called out by the class of oscillator. And for example, and this is just an example, if we're interested in 6 nines of acceptable shipping on 99.9999% of the product need to meet this requirement, then we would go out to this line shown here, and there's a positive deviation as well as a negative deviation. And inside of those 2 solid purple lines, we would call that the window of uncertainty. That with this given percentage of error, 1 micro% essentially of error, we're going to be inside of this window of uncertainty. And then the applications, from my understanding, the applications benefit by knowing at any given instant during a holdover what the window of uncertainty is. This model actually flows nicely into serving that requirement, because if we know M max and sigma max is a function of time, then the NIC card or somewhere in the system can communicate that to the server, to the applications running on the server, and they can actually compute, per application. Maybe each application has its own window of uncertainty that it likes to operate in, and they can change this crest factor 4.754 to whatever their application level quality needs to be. So I'm thinking that, and this is really a question for the group here, the way that I started out the discussion is that we're going to specify this Emax value, the maximum time error, up into and including the time holdover time, tau h, at a given PCB. Rather than making that part of the classification specification like I showed you on the Word document, maybe what we do, and this is a question, is here, I'm showing that as the dot. So today, the way I've framed it before this slide is we have this one requirement for Emax at a given holdover time, which is the x-axis value. Maybe rather than do that, maybe the classes of oscillators call out the methodology that we need to do in order to measure holdover, and then leave it up to the operators or even the application layer to use the information that the network communicates to the application to figure out whatever the application wants to figure out. But we essentially provide these lines here. We provide Mmax as a function of time and sigma max as a function of time, and let the system compute these values based on whatever their requirements are. Anyway, that's just a thought. So that's what I have here. Rather than spec this, should the spec just require the oscillator vendor to report Mmax and sigma max versus time? And this will allow the specs to not be hard-coded, but to be dynamic. And it provides full transparency for the oscillator manufacturer to provide the world what their device is capable of doing, and then let the world decide how they want to implement it, rather than having a hard-coded spec that may be applicable for Facebook, but not for Google or vice versa. Anyway, that's just one thought that I had. I'd be interested in people's feedback. Any thoughts on that?
I think it's a better way of doing it. Certainly gives some freedom to the individual operators then for their systems.
And then, Intel or Broadcom can have their own requirements. All you would need to do at that point is you need to fill out this form for what you're looking for in your application. And then based on the data that's showing here, all of this is input to the post-processing model that you would hand to the oscillator vendor. They would crunch it, or maybe we could even have an open source tool that is available to anybody to crunch. You just get the data from the oscillator vendor, and you can crunch the data and show what those values for sigma max and the Mmax would be, and then calculate the total holdover that you would have at any instant in time. entering holdover. So I see it as a much more flexible methodology that people don't need to get locked down into an exact number for holdover, which could change depending on the operator, depending on the data center, depending on the application running in the server. Each one of those, may have its own set of requirements, and this would enable all of those, enable a very flexible system. But this is just something I thought about in the last week, and I haven't even brought it into the oscillator work stream yet. So I thought since everybody was here, we could get an idea of what, whether it'd be interesting, because it's a little bit outside of my area of expertise at the application level. Any other thoughts, comments? Okay, then I'll go ahead and talk about next steps. So in the future, looking forward, we're going to provide the initial spec for the oscillator classes. I'm hoping to do this by the end of 2021. And I encourage everybody to provide your feedback in this process. And then we're going to revise the specs because we have a limited number of classes that we're looking at today. Essentially, we have one open grandmaster, we have a transparent clock, and we have a ordinary clock set of specs. But I anticipate that there'll be more, and then we'll revise the specification first quarter next year and submit an update to that specification. And then in parallel, we've proposed this holdover test methodology, but we still need to prove it out with data. We need to show that when you measure the actual holdover of a device and then you predict it based on this model, that the two agree within some acceptable margin. And this is going to be an extended series of tests that we're lining up now. We hope to complete this by the end of the second quarter next year, at which time we would write a white paper documenting the methodology to provide full transparency. And like I said, we would also like to provide an open source GUI where the community can use it to simplify all the, abstract away all the complexities of the statistical analysis and everything else. You just input the variables that describe your application, you input the test data from the oscillator manufacturers, and you have full transparency as the capability of that device and holdover. And I suspect it'll take us a month to write that paper, so targeting July. And then we have the spec itself for the holdover test method, which will take another month. Once we collect all the feedback, we write it up into a test document, and we publish that through OCP tab. So the call to action is that we would love everybody's feedback. We encourage your participation in the oscillator workstream. We meet once a week. All of the oscillator workstream meetings are already online. If you go to the OCP tab wiki page, you can look at all of the meetings that we've had in the past, and they're all recorded, and they will be in the future as well. And other than that, we encourage you to subscribe to the OCP tab mailing list. Take a look at the Open Time server on GitHub. That has been available for some time, and that's the model that we use for the Open Grandmaster. That's about it. Any questions?
Gary, a couple of questions. As far as the individual test methods for things like aging and, in particular Wander, have you guys given consideration to what spec you're going to use for Wander and what your windows are? Are you going to use ADEV, all that type of stuff?
Yeah, that's a good question. When we set out to do this, the consensus was that we would have individual test specs for aging and for what we call this DFDT. It's derivative of frequency with temperature, and Allen deviation as well. Those are more sufficient. They're more necessary but not sufficient. In other words, they're a course level spec that you have to meet this daily aging, this Allen deviation, and this DFDT. But ultimately, what matters to the end application is the holdover performance. And any way that you want to summarize, that you want to add those three noise processes together should be a valid path as long as you meet the holdover. So the holdover is the necessary and sufficient spec. It's the fine level spec that you have to meet. So yes, there is a coarse level spec for aging and Allen deviation, but that's just to make sure that you end up close with the right level of a class of oscillator. The actual absolute spec that you have to meet is holdover. And that one, we don't want to unnecessarily restrict people from having too tight a daily aging spec as to preclude a specific class of oscillator. For example, if a TCXO can meet the holdover spec, we don't want the aging to preclude it from being used in that application. Anyway, that was the original thinking. So yes, there are specs. They're easy specs for each of the noise processes alone, but ultimately the most difficult spec is the holdover spec.
Right. The other question I have is, are you defining a loop bandwidth on these things? Because the loop bandwidth and the Allen deviation are going to be critical to defining the frequency going into holdover.
Yeah. Yes,
So,
that's exactly right. We do have a parameter that we're calling the training time, and other people call this calibration time or learning time. So maybe training is not the best.
yeah, that's kind of different. That's to let the oscillator meet its stability. I'm actually talking about the loop rate of the actual disciplining circuit that you're using on in a GPS. You know, how often the GPS is updating the oscillator, because that's also going to wind up limiting where FO is going to wind up being. If your loop bandwidth's only, 0.01, you're only going to be able to update the oscillator once every 100 seconds, which means you're going to be limited by the Allen deviation at 100 seconds as to how good your loop is.
Yeah, so that is wrapped up in what I'm trying to attempt with this training, this tau training. So there's a separate consideration, which is you need to let the oscillator stabilize over time. That's not captured here. That's just assumed that it needs to rest long enough to be stable. But what this training time translates to in our model will translate to the initial frequency offset, which relates to the average frequency as observed by the servo. So the bandwidth of the servo is captured in here.
Right.
Yeah.
Well, thanks.
That's the only place that it intersects here. And yeah, so that'll help us establish the initial frequency entering holdover, which is, potentially a dominant source of holdover, dominant noise source.
Well, one question, Gary, like in short, like what's the best, I mean, not best, like what do we have today as a good, let's say, scalar to describe holdover?
What do you mean by scalar?
Like a number that you can use to describe the holdover of an oscillator.
I don't think that there's an analog. I think it's just holdover. I mean, holdover is a combination of multiple noise sources. So Allen deviation, which you can consider as wander, or thermal drift, or daily aging. Each of these combine in different ways depending on whether it's an XO, a TCXO, or an OCXO, or double of an OCXO, or atomic clock. And I don't know that we can. I don't know that there's a proxy for holdover other than holdover.
No, I don't mean a proxy. I mean, you given, let's say, oscillator 1 and oscillator 2, and you want to have let's say, a quantitative comparison. And then not only you want to do a comparison, you want to basically put them in a scale. So what would you suggest today as a scalar to describe that?
I mean, I think what other industry standards have done, like the whole stratum levels with the telecom industry, is one attempt to do that. Is that closer to what you're referring to?
The stratum is more a class, but so like basically, let's break it more into, let's say, details. Let's say when you look at the holdover, it's always a quadratic drift, like from a set point. So are there, let's say, some measures, like, or some values you can describe this behavior rather than like going on a ADEV like chart and then looking like, I don't know, how things are deviating and so on?
Are you talking about whether it should be like expected that it would be a linear change over time
No,
versus
of course
quadratic?
it's a quadratic because it follows entropy. But I'm just saying, like, in terms of description, like, what do we have today, like, in terms of scalars describing that? Or we don't?
I'm not aware. Maybe somebody else in the audience knows. I'm not aware.
Hi, this is Ned. Gary, there is one way that some people describe it is basically the ability to hold, say, 1 microsecond over a certain duration. So if you assume that ideally you're at point zero when the holdover event happens, then you specify certain references as basically being able to hold over 1 microsecond over 24 hours or over 8 hours. So that is one way I think is close to what Ahmed is asking for. Does that make sense? Or
Yeah, that makes sense. My problem though with like that region after, like, basically I love the scalar of this is like time over time, you know. So let's say after a certain amount of time you're within this, it's all statistical. So I mean, of course the whole process is a statistical thing because you're looking for a horizon of prediction. So I was just wondering, like, is there anything better still done there, or we're still at the same place?
as far as I'm aware, I think that was the closest, and it was basically fed with the idea that if you had an event and you had to basically fix something, you specified, say, 8 hours or 24 hours for maintenance, and the maximum that you specified, say, 1 microsecond, was basically, in the old days of Sonnet SDH, was basically the maximum that basically your buffers, so it doesn't overflow. So it came from that. I don't know if it's, I know what you're trying to kind of get more of a, you know, a measure that kind of allows you to trade off certain things, but
Yeah,
that is the
absolutely.
closest I know of how people describe holdover without having to basically look at what Gary was doing.
Yeah, because in dynamic systems we have some scalars that they can describe, let's say, Brownian motion behavior, and I see holdover is definitely a Brownian motion, and so I rather go for something like that because, let's say, I get an oscillator and then the manufacturer is telling me, yeah, you can expect under 1 microsecond for, let's say, 12 hours. And then I go and do the, like, I don't know, the test, and I see I surpass, let's say, 1 microsecond in an earlier time or something. And I reach out and they will be like, oh no, you need to have an ensemble of a lot of, like, let's say, iterations. And then statistically you will have, let's say, I don't know, P69s or whatever under, like, that's basically what Gary also was showing. And you can buy time more, let's say, on the experiments if you run a lot of, let's say, setups at the same time in parallel. So I still think there is something stronger here that can be, let's say, used to describe the behavior of, I mean, and I know the limitations we have, let's say, with statistics, but there might be something. And that's always probably, this is the question I always ask Gary about. So
Complicated.
yeah.
I mean, even the different classes in EXO, you're not really going to notice, depending on the quality, the Allen deviation in EXO because you're dominated by thermal drift.
Yeah.
And then you eliminate that in the higher classes of oscillators, and you notice other noise processes start to take over. So it may vary depending on the class.
Yeah. And this just reminds me to a talk we had about 5-6 months ago from forgot the name. Like, you can read it on the wiki. There were two talks. Anyway, so next in 2 weeks we're gonna have, I think, med you will present, right?
Correct. Yeah. Yeah.
Wonderful. So any spoiler or anything you want to sneak peek?
Yeah, I think I was as I was discussing with you. I think probably for the group it would be useful to kind of cover a lot of the ground on synchy and synchronization. Initially, I was going to do a little bit of kind of results from the tests, etc. But I think it's early in the process, and it might be good to basically give a backgrounder on synchy synchronization in general, and basically how it might apply, and hopefully with the feedback from the group, maybe later on if we want to do some practical results. And I think there's a lot of activities going, so maybe it's a little too early to go into the practicality and just see how is synchy, and this might actually fold in nicely with what Gary and team are doing in terms of the references, etc. Does some of the options, do we want to use some of the synchy, all of it, none of it, and hopefully that give people a good backgrounder on what's going on in there, and be useful.
Thank you very much. Thank you. We're on top of the hour, and if there's no more question, see you all in 2 weeks then. Okay. Thank you.
Thanks,
Thank you.